Okay, so let's go ahead and get started here. Today we're going to be reviewing factorizations and more LCM and GCD stuff. So this time I actually added a little more to the presentation. So let's start off with more LCM and GCD stuff. First of all, can everyone hear me? Okay, cool. Okay, so let's go over one thing that we need to know for LCMs and GCDs. So given any two numbers, m and n, then the following equation always holds true. M times n is equal to the GCD of m and n times the LCM of m and n. And if you think about it, then this is actually true, because remember last time, in order to find GCD, let's say that the prime factorization of m was p1 to the a times p2 to the b, etc. And n was p1 to the c times p2 to the d, etc. Then the GCD is found by taking the least of a and c and the least of b and d. And the LCM is found by taking the greatest of a and c and the greatest of b and d. So when you multiply them together, you actually include both of the exponents of a and c and b and d. And that's the same as multiplying m and n together. So you should probably memorize this formula. Yes, I can give an example. So let's say, okay, so let's use, let's use m equals 18 and n equals 24. So can anybody tell me what the GCD of 18 and 24 is? What is the greatest common divisor that both 18 and 24 have in common? Well, if we follow what we did before, 18 is equal to 2 to the first power times 3 squared, or 2 times 9. 24 is equal to 2 cubed times 3 to the first, which is 8 times 3. So remember, when we're doing GCDs, we always take the least exponent. So when we compare 2 to the 1 and 2 to the 3, the least one is 2 to the 1. And when we compare 3 squared and 3 to the first, the least one is 3 to the first. And 2 to the first times 3 to the first gives 6. So we know that the GCD is 6. Now, can you guys find the LCM? Well, just as we said before, 18 is 2 times 3 squared, and 24 is 2 cubed times 3 to the first. So if we take the greatest as opposed to the least now, 2 to the third is greater than 2 to the first, and 3 squared is greater than 3 to the first. And that gives us 8 times 9, which is 72. So the way I like to think about it is when you're doing GCDs, G is greatest. So you do the opposite of that and you take the least exponent. And similarly for LCM, which says least, you take the greatest. So we have 6 and 72. So what happens when you follow this equation and multiply 6 and 72 together? Well, what is 6 times 72? Well, if we do a little math on the side here, 72 times 6, you get 432. And what happens, since remember, m is 18 and n is 24. So if we look at the left side of the equation now, what happens when you multiply 18 and 24 together? Can anybody tell me? Exactly. It's the same thing. It's 432. So that's just a little example to show how this equation works. So does anybody have any questions? Okay. So another thing I want to show you is the Euclidean algorithm. So the Euclidean algorithm says that for any integers m and n, then the following holds true. The GCD of m and n is always going to be equal to, let's say that m was greater than n, then that's always equal to the GCD between m minus n and n. Well, an algorithm would basically be a series of steps in which you can find the result. So this would be one of the steps. So for example, can you use this property to find the GCD between, let's use our previous example. Let's say m was equal to 24 and n was equal to 18. And what is the GCD of 24 and 18? So if you use the blue boxed equation one time, what do you get? You would get the GCD between m minus n, which is 6, and n, which is 18. Well, at this point, you could probably already tell what the GCD is, but let's say you went one step further. And you said that the GCD of 6 and 18, if you use the same rule again, is the GCD of always the smaller one and the difference between the bigger one and the smaller one. And if you used it again, the smaller one is still 6. So you would get 6 and 12 minus 6 is 6. And the GCD between 6 and 6 is obviously 6. And that is basically the Euclidean algorithm in a nutshell. So does anybody have any questions? Okay, so let's move on to some problems. We already did some of these. I think we did this one, this one. I'm going to skip over this one because this one's easy. Okay, how many odd factors does the number 42 have? So I'll give you a few minutes to solve that. Okay, so if you factorize 42, then what you'll get is 2 times 3 times 7. And keep in mind, since they're asking for odd factors, then anything with 2 is immediately excluded. Because 2 times anything is an even number. So we must not have a 2. And then you can decide between 3 and 7. These are both to the first powers. And yes, 1 is an odd factor, so 1 would count here. So 3 to the first times 7 to the first. Well, for each number, the exponent can be either 0 or 1. And that means for 3, there are 2 options. And for 7, there are 2 options. And 2 times 2 is 4. So if you wanted to list these all out, then they would be 1, 3, 7, and 21. Okay, let's move on to the next problem. What is the GCD between 819 and 504? So this is a Euclidean algorithm problem, and I'll give you a few minutes to solve this. So the algorithm basically says that given two numbers m and n, if you have a problem where you're asked to find the GCD of the two numbers m and n, that's the same as finding the GCD. Let's say that n was the smaller number. You keep the smaller number, but then you subtract the larger number and the smaller number. So finding this would be the same thing as finding this. And since you essentially just made the number smaller without changing the problem, this actually simplifies everything. I see one correct answer. I'm just going to start writing the solution on the board. Oh, I see another one and another one. Okay. Okay, so let's get started here. So we're asked to find the GCD between 819 and 504. So when you use the Euclidean algorithm one time, 504 is the smaller number. So this is the same as the GCD between 504 and 819 minus 504, which is 315. And if you use the algorithm one more time, 315 is the smaller number. And the difference between these two numbers is 189, if I'm correct. Okay, and the smaller number here is 189. And 315 minus 189 is, let's see here, 126. And 126 is the smaller number. So the GCD between 189 and 126 is 126, comma, the difference between them, which is 63. And at this point, you could probably tell what the answer is, because since 126 is 2 times 63. But let's just go another step. GCD between 63 and 63 is equal to 63. So that's our answer here. Oh, whoopsies. Okay, so okay, we accidentally went too far in the presentation. Okay, so now we are going to go over divisibility rules. So most of you probably already know these, so I'm just gonna review them really quick and we can go over to challenge problems. Oh, what the heck just happened? Here we go. Okay. Okay, so to check if something is divisible by 2, then you have to check if the last digit is an even number. I'm pretty sure you all know that. To check if something is divisible by 3, then the sum of its digits has to be a multiple of 3. To check if something's divisible by 4, the last 2 digits have to be combined, have to be a multiple of 4. To check if something is divisible by 5, then the last digit has to be either 0 or 5. To check if something is divisible by 7, this is actually one of the more complicated ones. You have to double the last digit and subtract it from the rest of the number. And to check if something's divisible by 8, the last 3 digits has to be divisible by 8. By 9, the sum of the digits of the number has to be a multiple of 9. With 10, the number has to end in a 0. And with 11, the alternating sum of the digits has to be a multiple of 11. So is this a new material for everyone, or do you guys already know this? Oh, for numbers like 6, there is actually no divisibility rule for 6 because 6 is just 2 times 3. And if something's divisible by 2 and something divisible by 3, then it's automatically divisible by 6. And just to be clear, divisibility by 11 is, let's say I gave you a number 1,331. So alternating digits would mean 1 plus 1 minus 3 plus 3 minus 1. And if this number is a multiple of 11 and 0 counts, then the original number is divisible by 11. Well, there are rules for numbers above 11, but in AMC 8 and Math Counts Level Contest Math, this is all you need to know. 7 is, okay, hang on. So 7 is you double the last digit and subtract it from the rest of the number. So for example, 343. If you double the last digit, that gives us 6. And do 34, which is the rest of the number, minus 6. That gives you 28. And 28 is equal to 4 times 7, which means that this original number is a multiple of 7. The rule for 9 is if you add all the digits of the number, for example, 243, if you add 2 plus 4 plus 3, that gives you 9. And since 9 is a multiple of 9, this number is also a multiple of 9. Any other questions? Uh, 11 is, we covered that just now. You would take the alternating sums and differences of the digits, and you have to get a multiple of 11 in order for the original number to be a multiple of 11. 8 is the last 3 digits of the number is a multiple of 8. So for example, if I had a really long number, A, B, C, D, E, F, a 6-digit number, then if D, E, F as a number is a multiple of 8, then the original number is a multiple of 8. And the reason that a lot of these rules work is because of modular arithmetic. So we'll get to that in a later class, because this class we're just covering divisibility. You don't really need to know the rules for numbers higher than 11. 13 you might need to know. 7, 11, and 13 can actually be grouped together, because I believe there's a rule that encompasses all 3 of those numbers. But you really don't need to know that kind of stuff for math counts level contests, unless you're working with like really big numbers. Okay, so let's move onward. Okay, is the number 1039489281 divisible by 3? And is it divisible by 9? 9, I think that says, yeah. Someone asked about if a really big number, how to check if a really big number is divisible by 7. Like I said, there's a rule for 7, 11, and 13. I believe it's that you alternating add and subtract triplets of 3-digit numbers, but don't quote me on that. Okay, so let's go over this problem. Okay, so the divisibility rules by 3 and 9 both involve adding the digits of a number. So let's do that. 1 plus 3 plus 9 plus 4 plus 8 plus 9 plus 2 plus 8 plus 1. So you could choose to add all of these numbers together, or you could try to group them. So for example, if you want to check if it's a multiple of 9, you notice that there's a 9 here and there's a 9 here. And adding 9 to anything doesn't actually change its remainder when it's divisible by 9, divided by 9. So you can ignore those. 1 and 8 also combine to a 9. And 1 and 8 here also combine to a 9. So you're just left with 3, 4, and 2. And those add up to 9. So we've confirmed that this number right here is divisible by 9. And if it's a multiple of 9, then it's definitely a multiple of 3. So the answer is yes and yes. Okay, next problem. Is the number 1987349827 divisible by 11? Well, what we can do is we can just use the rule and, okay, you got the answer right there. But we can use the rule plus 1 minus 9 plus 8 minus 7 plus 3 minus 4 plus 9 minus 8 plus 2 minus 7. So plus 9 and plus 2 here add up to an 11, so that doesn't change the end result. You have a plus 8 and a plus 3 here, which also doesn't change the end result. Minus 7 and minus 4 doesn't change the end result because it combines to a multiple of 11. And you are just left with 1 minus 9 minus 8 minus 7. And if you end up calculating this, then it's not a multiple of 11, which means the answer is no. Okay, next problem. Is the number 32116248 divisible by 12? Well, to check if something is divisible by 12, then we have to break 12 down into its factorization. So 12 is equal to 2 squared times 3. So we basically need to check if it's divisible by 4 and 3. So this number is divisible by 4 because using the rule, the last two digits here, 48, is a multiple of 4. And now we check if it's divisible by 3. Well, when we add all of these digits together, the 3 here doesn't change the end result. The 6 here doesn't change the end result because it's a multiple of 3. 2 plus 1 is 3, which doesn't change the end result. 1 plus 2 here is 3, and 4 plus 8 is 12, which is a multiple of 3. So since it's divisible by both 4 and 3, then it must be a multiple of 12. So the answer is yes. Okay, let's move on to the next problem. Find all values of a such that the number 3124a is a multiple of 6. So let's see who can solve this one first. Remember it says find all values, which means there might be more than one. Okay, so To check if something is a multiple of 6, since 6 is 2 times 3, we need to check if it's a multiple of 2 and 3. So in order for it to be a multiple of 2, the last digit, which is a, has to be an even number. So that already narrows a down to 0, 2, 4, 6, or 8. So then to check if it's a multiple of 3, we need to add all the digits up. So 3 doesn't change. 1 plus 2 is 3 doesn't change. And 4 is 1 mod 3, which means that really we're only, the sum of its digits mod 3 is 1 plus a. And in order for this to be 0 mod 3, then a has to be negative 1 mod 3. And the only numbers that work are 2 and 8. Does everybody understand what a mod is? Okay, so a mod is basically a remainder when you divide it by a number. So, for example, here, 8 is congruent. This symbol means congruent. It looks like a triple equal sign to negative 1 mod 3. Because when you do 8 divided by 3, you get a remainder of negative 1. And technically, when you divide it, you get 2. But 2 and negative 1 are the same, since you can add 3 to 1 to 1 to get the other. We'll go over this in more detail if we have another number theory course. Okay, next problem. Find all values of a such that the number 9, 6, 7, 8, 0 is a multiple of 2, 3, 4, and 6. Keep in mind, a can also be 0. It can be anything from 0 to 9 since it's a digit. Okay, I'm just gonna, since we're almost out of time, let me just start doing the problem. So 6 here is 2 times 3. So if something's a multiple of 2 and 3, then it's automatically a multiple of 6. So we don't need to consider that. And we actually don't need to consider 2, because if something's a multiple of 4, then that means it's also a multiple of 2. So we can get rid of the 2 here. So we're just left with 3 and 4. So let's add all of the digits up. 9 and 6 are both multiples of 3. There's 0 mod 3, so those don't count. And 7 is 1 mod 3, since it's 6 plus 1. So we get that 1 plus a has to be 0 mod 3. And the last 2 digits here has to be a multiple of 4, which means that a0 has to be a multiple of 4. And if you think about it, if a is 2, then it's a multiple of 4. And technically 0 works too, since 0 is 0 times 4, so we'll include that. If a is 4, 6, or 8, then a0 is a multiple of 4. And since this gives us that a has to be congruent to negative 1 mod 3, then which number in this list is 1 less than a multiple of 3? Well, 2 is, and 8 is. And those are our answers. So any questions on that? We include 8 because 8 is actually -1 mod 3. Because 1 more than 8 is 9, and 9 is a multiple of 3. And if you plug 8 back into our original number, then you find that 96780 is a multiple of both 3 and 4. Mod is what happens when you divide a number and find its remainder. I'll go over this in more detail if we have another number theory course, but basically it means if A is congruent to B mod C, then that means that the numbers A and the numbers B both leave the same remainder when you divide them by C. And this is basically a congruent sign, which is a fancy equality sign. Okay, so we're almost out of time. So we have one challenge problem here. Find the prime number P such that there are integers A, B, C, and D, which satisfy the following system of equations. Okay, so you guys have a minute to do this. So let's see who's the first one to get it right. I probably don't have enough time to actually present the solution to this, but I'm just going to say, as a hint, add all of the 4 equations together and see what you get. Okay, so before we go, so today we covered a lot of number theory topics. And before it closes, let me just remind you that we have a YouTube channel that you can subscribe to, and you can check out our website at alphademic.org. So goodbye, guys. The channel is called Alphademic Learning. The problem will be in the video, which will be on Classroom, so yes.